Okay, so here is a video for class 13, our collection of videos. And we're starting chapter 6 of Sengel's fluid mechanics book. And we're going to talk about linear momentum. So here's a cartoon image of a wedded trying to hold a fire hose as it gets out of control. And this idea of momentum, linear momentum being applied to Reynolds transport theorem being applied to linear momentum is what's going to give us the concept of thrust. That's going to allow us to calculate things like a jet engine's thrust, at least in the introductory, preliminary, beginner kind. So here we go, Reynolds transport theorem. We've used it for mass, and we've used it for energy, and now we're going to use it for momentum. And then the next class, spoiler alert, we're going to use it for angular momentum. So we want to remember what momentum is. In many textbooks, they use capital L, and it's mass times velocity. And I often will say that for me, it's a van, by which I mean, as a kid, my family, we had 4 kids, so we had to have a van to get us to church and whatnot. And that van was an old decrepit thing, old Chevy van, and would break down. And sometimes you had to push it, right? Even as a 10-year-old. And you had to put your back into it, right? And really, really push, right? To get that van moving. So that force we were exerting on that van times the time, that was the impulse. And the van would slowly start to move. And then when it was moving, it was really moving, right? So like it's mass times its velocity. That thing is chucking along. And if you want to stop it, you have to run around to the other side and start pushing back on it. And it's hard to do, right? Because it's got some momentum. So you got to think of momentum as a thing, right? As sort of this quantity or this property that something can possess. And we can think of the mass as being we call it the inertia of the thing. It's its resistance to motion, but once it gets moving, once it has that momentum, we would have to apply some forces to get done. So Newton's law actually doesn't say F equals ma. It says the sum of the forces, or the net of the forces, when they're not equal to 0, are going to be proportional, or they're going to be related to the time rate change of momentum. We know if the mass is constant as part of this thing, and with time, the mass doesn't change with time. That's just F equals ma. But this is really the big idea right here. This guy, conceptually, is supposed to be a light bulb. Not a very good light bulb. But that's the concept right there. So as it applies, what we like to also look at it when it comes to using fluid mechanics, we want to apply the big D, which is the material derivative of the entire thing. And that's going to be equal to the sum, and this is going to be of the system, right? And that's a particular mass compared to us in fluid mechanics. We want to look at as things pass through a control volume. So that's what our Reynolds transport theorem is really doing. And remember, we have this big B, and that big B for us is going to be mass times velocity. I'm going to use the big V for mass times velocity. But we're transporting stuff. We're using mass to transport it, right? So here's a collection of mass per time right here. So there's this is our stuff per mass. So we want to divide the stuff that we're using it and just have that. Sorry, so mass times velocity divided by mass. It's just going to be the velocity. So that's our stuff, and we're using the mass times the m dot, which is really this thing right here, right? That's our mass flow. We're using our mass flow to transport our stuff, which in this case is linear momentum. All right. So if we want to write out the big equation for this, and let's do it. Let's take a whole bunch of sums of masses and for the system, right? So there might be multiple ones. So we'll take it to velocity, and we'll distribute its mass. right here. So that's going to be, there you go there. And the density could potentially be different and whatever with time. So we have this over here on the left-hand side represents the same thing as right up here. So that's going to be equal to the partial derivative with respect to time of what's happening within the control volume. And so that's going to be this velocity times this mass right here. And that's going to be momentum, but then we're going to take the time rate change of it. So whatever happens here is the rate of change of the linear momentum inside the control volume. And we're also going to say, well, what's coming into and out of the control volume? That's going to be through the control surfaces. And here's our B right there. So that's representing this right here times our density and then times the velocity dotted with the unit normal vector that's pointing outward from the control surfaces, right? So seems like a little weird because we have a velocity and a velocity. We almost want to square them, but note, we want to do this dot product first, and that's going to create a scalar. Remember that this portion right here is actually m dot, right? And then that's going to equal the summation of forces on the control volume, noting that for an instant in time, the system and the control volume are going to be the same thing. So that's what we have right in here. So that's the rationale. So this right here is really our main equation, the one that that is a consequence of the Reynolds transport theorem. We note that we often have a situation where we have steady flow. So in steady flow, there's not a change inside the control volume. That means at any given time, when it's steady flow, you can take a snapshot now, take a snapshot later, everything's going to be the same. So what we have here is I like to bring this over onto the left-hand side to say the sum of the forces on the control volume are going to be equal to the integral across all the control surfaces of the velocity times the density times the velocity dotted with that unit normal vector, dA. And if you're paying attention and reading the book, which you should, it's a good book, Sengel's good book, 618. It's equation 618 in your textbook. If you want to learn more about it, get more here, some more derivation steps that I'm not including here, I'd encourage you to jump in there and read this section right there and then look. But this is the thing we're going to get to. And this is the big idea behind thrust, that the net force is equal to the net rate of flow of momentum across the control surfaces. So you can think of like jet engines or even a rocket engine and the thrust that gets generated by them. But there's all kinds of other things where this plays a role. And so these forces, by the way, are all kinds of forces. They could be surface forces, which include pressure acting onto the surface. They could be viscous forces because this is not Bernoulli here. We could have viscosity involved right here. You could have other forces. I just maybe not creative enough to come up with new ones. We could also have body forces, right? So and there could be gravity. Maybe the thing has some kind of motion where it's centrifugal forcing. So there could be some things along this. There could actually be acceleration, could actually be inside there. You have to be careful with the directions of those, though, because now you need to think of those as inertial forces, and sometimes that's a little bit more complex. I don't want to break our conventions of dynamics, but there could be. We also might have reaction forces that are acting onto the thing. Which they could be the constraints. They could be the thing could be held down or something along those lines. So I have I think the next slide's coming up here. Oh boy, that's supposed to be an animation. Anyway, I should fix that. But I have the little thing I usually do, ask a quiz, and says who said I am and ever will be a White Sox pocket protector, nerdy engineer, born under the second law of thermodynamics, steeped in steam tables, in love with free body diagrams, transformed by Laplace and propelled by compressible flow. And that, our friends, is Neil Armstrong. He was not just a pilot, he was also an engineer. He was an engineering professor after his time with in NASA. So it's kind of an interesting thing if you're interested in aerospace. A fellow engineer, Neil Armstrong, been to the moon. So when performing any of these, we want to pick a control volume, and in my opinion, we want to treat it like a free body diagram. That's the reason why I brought this thing up right here. I emphasize free body diagrams. They are the heart and the soul of engineering problem solving. They're the probably most important tool we have at our disposal if you have a problem that you haven't seen before and you're trying to figure it out and involves something physical that's solid in this world. You should draw a free body diagram at any time you can, any chance. To try to think your way through and apply those critical thinking skills to the new situation in order to understand it and to get the signs right when you're trying to do a problem. So we want to pick our control volume and draw a free body diagram with it. So here's all this other stuff I've already mentioned down here. And so these forces acting on the control volumes, you can see this is also repetitive. You can see there's got these forces and this outward normal that are taking place onto the control surfaces. So you have the total force is equal to body force and the surface forces. So, and then here's another diagram of us applying that capital B, little b's to our Reynolds transport theorem. And this is what I said. Okay, so one thing that the Sengel adds in here that I don't see in many other books is something called a momentum flux correction factor. And that's really just sort of the idea that the velocity profile is not uniform across the many control surfaces. In fact, that's in some part because of the no-slip condition due to viscosity at the little chunks that are just adjacent to the boundaries will have no velocity, and then they're going to have maybe maximum velocity in the center. We usually end up using the average velocity when it goes across a control surface because we're trying to simplify problems. But one aspect that can cause some for momentum crossing here is it's not going to be equal to the average momentum is not going to be equal to the average velocity. Don't ask me why, actually, off the top of my head. I read this section because I'm never. This is sort of relatively new to me. But what we end up doing is we include a beta term in here, right? So one thing we should note is that beta is always going to be greater than 1, right? So it's always sort of a multiplier to and some of the ones that I've found were like 1.03, 1.05. So it's not a huge correction factor. And a lot of books leave this out. So it's interesting to me that Sengel chose to include it. A closer look, quick look at this equation right here. And let me see, what equation is this in our textbook? It's sort of I think it's equation 618. So did I already say that in my notes here? Did I write that it was equation 618? Yeah, I did. All right, it's equation 618. Right. So some of the purpose of this is first we're might be entering or exiting the control volume, and these are vectors, right? So we're going to be important. This right here is going to be a scalar, we should know, but it will have a sign, right? But when we break this down into x's and y's, or z's too, because they're vectors, we want to keep in mind that this can have a positive and negative sign. This can have a positive and negative sign over all the different forces that are in there. So the sign of this one is going to be dependent on which direction velocity is going. But the sign of this one is actually going to be dependent on whether these agree or disagree. And remember, that's an outward facing. So on this little figure that came from Munson's book, you'll notice that we have the outward normals right here. They're always facing outwards. But we have there's a velocity of stuff coming in, right? So notably, this is in the negative direction, and these are in opposite from each other. So this be a negative, negative. So when we go to accumulate this stuff, this transfer through this control surface right here, that control surface, it'd be a negative times negative. So we actually have a net positive. Whereas these two are in agreement, therefore it's plus. And also this one's in the positive direction, so that would be plus. Here's some other ones, though, that might be not intuitive. These are going in the same direction, so they're exiting. So that's positive, but this guy is in the negative direction because he's in the negative y direction. So that's going to be a net negative, at least for this control volume. And these two are in the opposite direction. So almost draw this positive, I meant negative. So they're dot product against each other, which means it's 180 degrees. And we use the cosine sometimes of the angle between them. And so cosine of 180 degrees is negative. So these are negative, but this one is a positive, right? So this is a net right here, negative. So it's interesting. That's a negative and that's a negative right there. I think I got that right. So, so you really want to watch out for these signs. And to keep track of the stuff on the left-hand side of this, I say draw an FBD and of the things, right, the forces that are acting onto this. So we might have like a thrust force might be the thing that we're saying is going to be acting onto this whole piece. We could find out that the thrust force is going to be to the left because we're going to have, say, this is going to be out, and so we're going to have m dot v out. But we're also going to have an m dot v in. Right there, going on. I think I said that the wrong way. I think actually we're going to have like a drag force that's going to be acting onto this right here. Anyway, I don't think I'm making a very good point with this right here, because we have to decide whether this thing is accelerating. But I would draw this over here onto the right-hand side as my momentum diagram. And another book that I use has been doing this, and I think that's a really useful thing, this momentum diagram. So in all my examples, I'm going to be including this right here because it's very similar to how I teach dynamics, where I have an FBD and an inertial body diagram. Sometimes we call that an inertial response diagram, but this is the momentum diagram that we have over here on the right-hand side. So lastly, I'm going to leave you with the most important, the main equation that we'll end up being using. And that's going to be the sum of the forces on the control volume. And this is, we're going to make this for steady flow conditions. And let's also make it for a fixed control volume. Right? We're going to say the sum of the betas times m dot v out minus the sum of the betas m dot v in. And this is equation 625 in your textbook. A good thing to learn. The reason why we have the out minus the in is because of those relationships of the velocity and the outward facing normal unit vectors. Those are the things that give it this sign, generally speaking. So this is a steady linear momentum equation, and these are the velocities with the average velocity, and we have these beta, which is described right over here, the momentum flux correction factors. So there you go, right there. A lot of times it'll be looking like this right here for problems. So let's do some examples.